So if you are watching this video, congratulations, you have made it to the final lesson of the semester, the last new piece of content we need for semester one. And it's talking about a different kind of random variable called a geometric random variable. So what we'll need to do is we learn about this is compare and contrast it with a binomial so you guys can understand when each one is used. Both are great tools for analyzing probability. They just do different kinds of probability. So normally I would pick a student out of my actual class and make you guys put you on the spot and put you in this problem right here. But I figure in a public online video, I probably shouldn't use somebody's actual name here. So we've got good old Larry, and Larry is going to us with the gym. The whole class is going to the gym for AP Stats. And then we're not going to leave the gym until Larry finally makes a 3-point shot. So he's going to keep on trying until he finally makes a shot. We're going to assume that shots are independent, and we're going to say the probability he makes a shot is 0.125. So Larry, not the best 3-point shooter in the world, but that's okay. We're going to stare, cheer at him until he finally makes one shot. Could this setup be modeled in a binomial format? Let's look. So for this problem here, B, is it binary? Yes, it is. He either makes a shot or doesn't, so it's definitely binary. A success would be a made shot. Is it independent? Also yes. Again, we've talked about sports and how that's debatable, but yes, assumed in problem to be independent. Going to skip N and go to S. Is it the same probability of success? Yes, it is. You're going to have a probability of success of 0.125. And then the one that I skipped right here, is it a fixed number of trials? It actually is not. We have no idea how many trials it's going to take. It could be where Larry makes his first shot, we all cheer, and then we go home. Or it could be where Larry's having an awful day and misses 50 shots in a row, and we're sitting there after school just getting mad at him for not making his shot, and it's just a disaster of a situation. We have no idea going in how many trials it's going to take. That's actually what we're interested in this problem here. And this is actually the difference between a binomial setting and the new setting right here we're going to talk about called a geometric. So I want to make note of that on these slides. It is not fixed. We don't know how many trials it'll take. And that's what makes something a geometric setup. The other three conditions, B, I, S, all are the same, basically, but your number of trials is not fixed ahead of time, and that's what makes it geometric. So let's actually define this scenario right here. You have to be able to understand the difference between a binomial and a geometric. Binomial counts the number of successes. How many shots am I going to make out of a set number? Out of 20 shots, how many will I make? That would be binomial. Geometric doesn't count the number of successes anymore, though. What a geometric does is it counts the number of trials. So it's the number of trials, not the number of successes, until the first success. So in a geometric setup, as soon as you get a success, we all go home. Problem over. You look till you get that first success, but you're counting how many trials it takes to get there instead of how many successes you're going to have. So thinking about the number, like the possibilities. In a binomial setup, binomial, remember, is the number of successes in n trials. And with a binomial, you could have no successes or one success or two successes, etc., all the way up to n successes, number of trials. With a geometric, we're going to count the number of trials until the first success. So a geometric could not equal 0. You'd have to have at least one shot before you can make one. So the lowest possibility is 1 as opposed to 0. And when you think about how many options are possible right here, there's actually never an official stopping point. It could take him a million shots until he finally makes that first shot. You don't know. So there is no end points for this. It just keeps on going. Okay? So there are differences between binomial and geometric. So let's talk about how you would actually calculate a probability. We're going to let y equal the number of shots required for him to make a three-pointer. So y is a geometric random variable. How many shots till he makes one? What is the probability that y equals 6? So we have to think about what this is actually saying. And again, we're just working through what we understand about probability here to get our answer. In order for it to take him 6 shots, okay, y is 6. 6 shots to get a success. What had to happen on his first shot? Well, he had to miss it. If he made the first shot, we would all go home. We wouldn't have been around for shot number 6. So we know that his first shot would have to be a miss. If there's a 0.125 chance that he makes it, there's a 0.875 he doesn't. So he has to miss the first shot. Well, he also has to miss the second shot, because if he made the second shot, we would go home. He would also have to miss the third shot. He'd also have to miss the fourth. He'd also have to miss the fifth. If he made any of those, the problem would be over. And then on that glorious 6th shot, he finally makes it. We'd have a 0.125 at the end for that made shot. So in other words, what we're going to have here is 5 0.85s, 0.875s, followed by that made shots. If you multiply that out, so I have 0.875 to the 5th power times 0.125, you're going to get 0.064 for your probability. Now you might ask, well, what about that like combination thing in the front? The thing about a geometric is it can't happen any other way. There's only one way it can happen, because if I put this guy, the made shot, right there, for example, then I don't need those shots anymore. The problem just ends right here. So there's only one way it can be set up, which makes the formula a little bit easier to handle than the binomial. Okay? So next problem says, what is the probability that it takes Larry at least 3 shots, or at least 3 attempts to make a shot? The thing about geometrics is, as I said up here, they do not have an end. It could, in theory, take him 10 million shots to make one. Probably won't. If he's a 12% shooter, it'd be like crazy unrealistic, but in theory, it could. So you can't actually mathematically do this. It's impossible. You have to treat it like the CDF problems on the calculator from last video and do a 1 minus. So what I'm going to do instead is think about all the stuff I want. I want 3, 4, 5, 6, 7, etc., which means I don't want a 2 or a 1. You can't be 0 in a geometric. So it's just these that I don't want. So I need to subtract out the probability y is less than or equal to 2. So I can just find these guys in green and then just do a 1 minus on it. What's the probability it takes him 1 shot to make his first shot? Well, it's actually just the probability of success. So the probability of 1 is quite easy. It's just 0.125. The probability he makes a shot is there. Then I think about what's the probability it takes him 2 shots. Well, he would have to miss, and then he would have to make to get 2 shots right there. And if you multiply that out, it's going to be 0.109. So I just have to add those together. And it's good to use the full decimal when you do add stuff like this in the calculator. And I do a 1 minus on that. So I get 1 minus 0.234-ish, which is 0.766. So there's a 76% chance that it takes him at least 3 shots to make one. All right, so let's keep it going here. The formula for a geometric is easier than the formula for a binomial because you don't have to worry about scrambling. It can only happen one way. And if we look at a geometric problem, there's actually only one thing you need to know. You have to know the probability of success. So in a binomial, there were two parameters, p and n, for number of trials. All you need in geometric is p. And if you think about it logically, this is saying the probability, it takes him k shots to make one, okay? So the problem starts out with a failure. You have to fail and fail and fail and fail until you finally succeed. Well, the probability of failure is 1 minus p. On my last example, I started out with those 0.875s for the missed shots. How many times do you have to fail? Well, if I'm taking 6 shots, I fail 5 times. If I'm taking 10 shots, I fail 9 times. You fail 1 less than your number of possibilities. So if I have to take k shots, that means I fail all but 1 of those times, k minus 1. Times on that glorious shot that you finally make, there's only 1 of those, so I'm just going to put a p. This is the formula for a geometric problem. And on our sweet formula sheet right here, they have that exact setup. They just used a little x instead. 1 minus p to the x minus 1 times p. It's actually kind of nice. On the formula sheet, they tell you the values that x can actually equal, which is handy. Just like with Binom, there is a Geomet's PDF and CDF in that same distribution menu. So you do have the option of using those. They're way at the bottom. So that's an option too. And same as before, when you do the PDF, or sorry, the CDF version, it always does always a less than or equal to, and this is for equals. So you have the option of doing that, but the formula, honestly, isn't that bad for geometric, so you may not even want to. You may just use the formula straight up. So let's talk expected value, and let's talk standard deviation. So the expected value for how many shots it's going to take Larry. The probability Larry makes a shot was 0.125. And if you're good with your decimals here, you should know that 0.125 is an eighth. So if you think about it logically, because it is a little bit logical with the mean here, if Larry makes an eighth of his shots, sometimes he's going to get lucky and he's going to take like 3 or 4 shots and he's going to make it. But sometimes it's going to be unlucky and it's going to take him 9 or 10 or 11 shots to make it. But it seems reasonable that if he makes an eighth of his shots, it'll take him an average of 8 shots to finally make one. And it turns out that is the formula, or the correct answer, for the mean of a geometric. It's 1 over p for your formula. So the actual formula for the mean of a geometric is going to be 1 over p. So in this problem, our variable from earlier was y. We're going to do 1 over an eighth, or 1 over 0.125, which just equals 8ths. So if we think about what that is saying, now you have to be careful how you word your expected value here. You'll be tempted to say like over many shots, but it's not the shots themselves. Like one go at this is a set of shots. So over many sets of shots where Larry tries to make one, the average number of shots it'll take before he makes one is 8ths. And I'll pause and write that down in slightly cleaner language. All right, so there's the wording right there. Again, I want to emphasize, people will just say over many shots because that's what we're used to doing. But in the geometric sense, a trial or like one go is until he makes it. So it's over many sets of shots until he makes one that you're worried about in this problem. So that would be a good interpretation of this. So let's talk about standard deviation. And again, I won't get into the justification of the formula. I'll just show you that it is on your sheet right here. So we have square root 1 minus p up top and just p, no square root on the bottom. And it's nice that you don't have to memorize these here. You can just look at your formula sheets. So that's just easy plug and chug. On this particular problem, the probability of success was 0.125. And if you actually calculate this guy, looks like you're going to get 7.48. So that's a pretty large standard deviation compared to what we saw like on some of those binomial problems we were doing. What is that? It means if you look at a randomly selected, like AP stats going to the gym scenarios here, if you look like a randomly selected day where Larry's going to the gym and shooting until he makes it, the number of shots it will take him is going to vary by a typical amount of 7.4 shots from the mean of 8. Why is it so much bigger? Well, there are days Larry could very easily make it on the first try. If he makes it on the first try, 1 to 8 is a difference of 7 right there. There could be days where he's just awful and not making them, and it takes him 20 tries. 20 to 8 is way more than 7 even. So there's going to be lots of times where you get that variability in that range going on. So I'll throw up a nice explanation of the standard deviation. All right, so you guys can see like a nice little explanation right there for the standard deviation, basically going through what I just talked about. The last thing in this lesson that we need to handle here is looking at the shape of a geometric, and we'll also talk about a binomial distribution. So basically, if we made a histogram of the probability distribution, what kind of shape would we see? In order to answer that question, we first have to make a little probability distribution table and figure out the different possibilities. So if you guys remember, when you're making a probability distribution, you need to know two things. You need to know what your variable is equal to, and you need to know the probability of that value. So in a geometric problem, the smallest answer you can get is a 1, or you can get a 2, or you can get a 3, or you can get a 4, etc., etc., etc. I'm going to go up to 6 right here. And we've actually done a couple of these already. For example, I know the probability for one shot is a 0.125 here. The probability for 2 shots, we did that one earlier on. That was 0.109-ish. And then we're just going to get these other ones taken care of as well. I'll show you guys where the button is, and then I'll just pause and throw up the rest of them. If I'm doing a PDF scenario here, I would do a p-value of 0.125 and an x-value of 3. And when I do that, it's 0.095 for my next guy, etc., etc. So I'll pop up those remaining answers. Okay, so I calculated through 6, and I threw in a bigger number of 20, just to give you guys an idea what's going on with the probabilities, and I transferred that over to a histogram, where I need to make sure I put labels. So I have y, and I have the probability. And if you look at this picture right here, you will see that the probabilities get progressively smaller as you go along. They are only decreasing in value as you go further along right here, meaning that this graph right here is actually skewed to the right. So a geometric random variable will always look skewed to the right when you actually graph it. Now, this is actually a little bit counterintuitive, but think about the following question. If I asked you, Larry's a 1 out of 8 shooter, that's all he makes, 0.125 is the chances he makes it. What's the biggest, like the most likely number of shots it'll take him? What's the highest probability for what he's going to actually do? You wouldn't guess, like if you had to bet on exactly how many shots it was going to take Larry, you wouldn't think so, but actually the best thing to bet, or the best thing to guess, is actually 1. Even though he's probably not going to make that shot, that value at 1 is the largest out of all of them. Why does that make sense? Well, every time you go deeper into your table, you'd have to get from here to here. You need another miss in there, which means every time you move down a number, you're multiplying by a decimal again and again and again. And as you guys know, when you multiply by decimals, your answer gets small. So obviously, this is not a very big probability at all. And the probability he won't make the first shot is pretty high, 87%. But in terms of like single outcomes, the most likely outcome is the first one, because you always multiply by a decimal to get deeper into your table. So what does this tell you about the probability as k increases? It always decreases. And then this is in comparison to a binomial. I didn't talk about this at the time, and our textbook goes more in detail on this, and it's good read just to be able to get a little bit of background there. But the shape of a binomial. So think about like we did our problem with the number of test questions you get correct out of 20, and the average ended up being like 4. What you'll end up finding with a binomial distribution is that if 4 is the average, that's the most likely possibility. And getting 5 or getting 3 correct is also pretty likely. And the farther away you get, the less likely it becomes. What you'll find, this isn't like a formal proof or anything like that, but basically, if certain conditions are met, binomial problems end up being approximately normal. We'll learn more about those conditions when we get next semester into chapter 7. But for right now, what I need you guys to just be aware of, binom can look approximately normal, certainly symmetric, approximately normal, and then geometrics are skewed to the right. So that closes out chapter 6.